Okay, everyone. Let's start the fifth lesson of AGN. But before starting, you know that the exam is arriving. No, it will be on the next week, on Wednesday. So you two for sure are doing the exam, right? I don't know about you. If you want to do the exam, you can do the exam. It will be to measure how much are you following the course. Okay, but it's on your as you wish. Okay. Okay. Let's. Yes.
It's an oral exam, right?
It's a,
Individual, or we have to everybody.
yes. This is okay. This is important.
Just like
No. Yes. It will be individual, and I will give you 7 topics among the things we discussed here, and you choose 5 to discuss.
So one person
at a time, exactly. So you two for sure during the class, during the from 2 to 3.5 of next Wednesday, you are going to do the exam. Okay. Maybe you can do first. Okay. You at 2 and you are at 2:45 more or less. Okay. And something else. Next class, I'm thinking to give a review. Okay, so you can get prepared to the exam, and it will be very important that you know how to derive some things, even if you think, okay, I will forget about this in 1 week. This is not a problem. Okay, the thing I want is that this kind of information pass through your mind and it stays there at least for a few days. Okay, so in the future you can you know more or less at least where to find this kind of information. Okay, in the last class we saw the temperature profile of the disk. Do you remember how it was more or less? Do you have a general idea of the shape? Yes, like that. So so in the inner border, it's a bit colder. Then at a fraction of, we saw 49 over, I don't know how many, 12 maybe, Schwarzschild radii. Okay, so we have an increase in temperature in the disk. We have the maximum temperature, and then it falls off as with R to minus 3/4. Okay, 3/4. And today we are going to see what's the emitted spectrum from this profile temperature. Okay. However, we have to do some approximations, otherwise we cannot arrive at any useful conclusion. So let's start by integrating the Planck black body emission in the solid angle. Here I'm integrating only the perpendicular component. Okay, that's why I'm putting this cosine here, while the sin d theta and d phi comes from the spherical integration. Okay, so imagine a section of the disk which is emitting black body radiation. It's at a constant radius, no? So every single ring in the disk emits as a black body. And we are integrating this emission in the in 1/2 of the sphere, okay, above the disk. Okay. So if you do this integration here, this will give you 2 pi. This integration here is in the angle, so you can put the b outside of the integral. If you evaluate this integral here in half the hemisphere, you have 1/2. Okay, so tack. At the end, you have pi times the Planck emission. This result here is the flux, the differential flux. So this is energy per second per area. Okay. Instead of it, the original Planck emission law is in energy per area per second per solid angle. Okay, we just integrated in solid angle. Furthermore, this was the formula that we found in the previous lesson for the temperature. We will do the approximation here of a large radii, and we will assume that as true everywhere. Okay, this is because if we don't do that, you see, we cannot solve the problem. Okay, doing that, it's very hard to solve the problem. So if you don't do that, it will not be useful. Okay, so we can take this approximation. R very large, this goes to 0, these brackets here go to 1, and then the temperature depends on the radius to -3/4. Okay, we can write this actually not very good in this. I'm sorry. This would be something we are missing. Our minimum there, so it would be like T dr is proportional to R to -3/4. However, we can normalize this by T max, which will be proportional to R. Let's call it R in. Okay, we are approximating the internal radius of the disk as the point where the temperature is maximum. Okay, if we don't do that, you see, we cannot solve the problem. So just to fix that, I'm sorry for that, but for this typo, but just to fix this relation here, this would be T max R over R in to -3/4. Okay, I'm sorry for that. Okay, let's see how we can compute the disk spectrum. We have to integrate over the two faces of the disk. So this 2 pi r dr times 2, because we have two faces in the disk. So we can recover the luminosity integrating in radius. We have this for the temperature. We can set U as R over R in, change the variables here, and we can write U in terms of temperature. If you take the derivative, you find this result here. And let me turn off the light, maybe easier here. And then we can change the limits. You have, for instance, here from 1 to infinite. Here would be T max up to T min. Okay. However, we have a negative sign here, and then we can simply switch the integration path, and then we can change the signal. Okay. Is it clear, or I was too fast here? Are you following? I'm just integrating the black body flux over one ring. Okay. However, I multiply by 2. Here was supposed to be 2 pi r. I multiply by 2 because we have two faces in the ring. Okay. Then the only thing I do is a change of variables, okay, to facilitate our lives. And at the end, I can write the luminosity as this bunch of constants times the integral of this black body shape curve. Okay, now let's try to solve this integral here. Okay, let's forget for a moment about the constants. Later we can come back to them, but let's try to solve this integral here. We start with a change of variables. So we can set x as these quantities, hν over kT, and then we can rearrange the integral. Okay, we can, yes, just putting it in terms of this x that we just defined. Then the integral will become this here after putting out the constants. If we collect the prefactors from the previous result, we arrive in this final form for the luminosity. Notice that we still didn't resolve the integral. No, we are just changing variables to make our lives easier. Here we can substitute T max, which we can write like that, as you saw in the previous lessons, and we can use this R in. You saw that. Do you remember, no, that the ISCO radius, the innermost stable circular orbit, is 3 Schwarzschild radii? Do you remember that? Schwarzschild radii, 2gm/c squared. So this is 3 Schwarzschild radii are in. We can substitute this here and T max here. Okay, and then you have this. This is the luminosity spectrum for a disk emitting in rings of black body radiation. But the problem is not solved. It's not solved. The integral is there. Now, solving this integral is not straightforward, and we have to do some approximations. Okay, let's do the first approximation considering very small values of x. So let's consider that the energy of the photons are much smaller than the temperature, okay, than the thermal energy. So in this limit, x min and x max are much smaller than 1. We can substitute that. This exponential here, exponential minus 1, will become just x. Can you see this? X minus x, e to x minus 1. You can expand this in Taylor. This will be 1 minus x, 1 plus x actually, and then the 1's cut out, and you are left with x. Okay, so you substitute here by x, the integral becomes this. This is feasible. We can work with this. This is the kind of integral I like to solve, and the result is simply this here. However, since x max is much bigger than x min, you can see that here x min is defined in terms of T max. So the maximum temperature in a disk is much larger than the minimum temperature. So x max is much larger than x min. Okay, so here you can cut x min, and then you have this result for the integral. Okay, substituting back in the formula for the luminosity, we see that the luminosity of the accretion disk at the regime of low energy photons is proportional to the frequency square. Okay, so let's start to see how this spectrum will become. So let's, here we have what we call Ni F d Ni, which is the differential luminosity, okay? And here we have the frequencies. This solution is for low frequencies, okay? So this means that at low frequencies, this is in log space, we have something like this, okay? The index here is 2, okay, as we see here. Luminosity is proportional to, actually, let me write this correctly. Is proportional to Ni to the power of 2, Ni squared. Now, the second case, which is the regime when we have intermediate energy photons. Now, we have that x min is much smaller than x max, which is much larger than 1. We will approximate x max as infinity, okay? So and x min as 0. When we do that, this becomes the integral of the gamma of a combination of gamma and Riemann zeta functions. Okay, so in our case, this S here, this X is 8/3, and we can simply solve in the gamma and Riemann zeta functions. Okay, this is a constant. This is a constant value. So for us, this is not changing the prefactors. In the prefactor, we had Ni to 1/3. Then we just have to add a constant. So here in the spectrum, what happens is that this strong increase will now become weaker for intermediate frequencies. So it will be like this. Okay. Following? Okay, let's see what happens for photons of very high energy. So in the very high energy regime, now Xmin and X maximum are much larger than 1. Exponential -1 is basically the exponential. And then the integral becomes this. Here, actually, we do a very dirty approximation. We do a sort of a delta approximation. We consider that basically all of the emission is in Xmin, in this case here. Okay, and then we can simply approximate by that. Okay, and substituting this in the equation for the luminosity, we find that the emission now drops exponentially. Okay, so finally, what we have here for very high energies is a cutoff, okay, an exponential cutoff. So this is the shape of the spectrum. We can do this better, and I will show you here in the next slide. So this is the disk spectrum for a supermassive black hole, 10 to 8 solar masses. These are the curves that we just derived. Okay, now let's change for a stellar mass black hole. Actually, for a 100 times lighter, it's not a stellar mass, but 100 times lighter black hole. You see that the luminosity decreases. However, what happens with the peak, the temperature peak? It shifts to higher energies. So the luminosity decreases, but the temperature increases. Okay. And I told you in the past lectures, I think that stellar mass black holes are much hotter than the disks of stellar mass black holes are much hotter than supermassive black holes. And yes, you can see the trend, no? They will be shifting always to the right here, but the luminosity will decrease, okay? Following? Ok? Paulo, repete tudo que eu disse aí. Eu falei brincando, mas vai, já que você começou. What?
With the decrease of, as the mass decreases, the peak will be shifted
To the right.
Luminosity will decrease as well.
The luminosity will decrease, yes. And did you follow the shape of the spectrum? Yeah. Why it's shaped like that? So we are taking 3 approximations. No? So actually this result here in the middle, the luminosity, the differential luminosity growing with Ni to 1/3 is a very, very useful result, and you find it everywhere in AGN astrophysics. Okay, and actually this is the cause of the big blue bump. You remember we discussed about the big blue bump? So if you have in this plot here, if you have a flat spectrum radio quasar with the 2 bumps, you remember the blazars have 2 bumps. If it's a BLAC, we don't see disk emission, but if it's a flat spectrum radio quasar, we can see. And we could have here, for instance, the synchrotron component here and then an inverse Compton component here. Okay, so what you would see was something like that. The summed emission would be something like ta, then comes here with the big blue bump, decreases, and then increases again towards gamma rays. Okay. Okay, but everything we did up to now was considering this special disks, thin accretion disks, purely hydrodynamical disks, no general relativity. We use it here, and this is useful, but it's not very precise. We can do more precise models, but these things are generally not analytical, and they are quite tough to understand. Okay. However, these simplified models gives us already some very useful concepts. Okay. So real AGN disks, they may include a non-uniform geometry, as you see there. They can have winds, magnetic fields for sure. Okay, so accretion disks will be embedded in magnetic fields, and this can change a lot the accretion. If we don't have magnetic fields, the efficiency of the accretion is negligible. Basically, no matter falls in the black hole. Okay, we need magnetic fields. This will be clearer in the next slides when I talk about magnetorotational instability. Okay, so we can have some sorts of blobs, some clouds going up in the magnetic field lines from the disk. These clouds can suffer pressure radiation from the disk, okay, or even from the corona that we can get there later. And you can, from this picture, you can understand that the mess just grows and grows. Okay. This step here is fundamental for the next slide, where I will talk about the corona. However, you can use this in several research topics. Is that how to measure the size of things, or at least put an upper limit on the size based on variability. Have you ever seen this kind of estimate of size? No. People working with light curves, with AGN light curves, typically use this a lot. Let me do another draw here. So let's suppose this is time and this is flux. Okay, so we have the light curve of an AGN, which is, let's say, it's quiescent. Okay, so if we take the variability time scale from here to here, from the peak, we can estimate the size, at least put an upper limit on the size of the emitting region. If you assume that this region is illuminated and reacts at the speed of light, then the amount of time that the region takes to go from basically from the quiescent state to a very highly illuminated state will depend on the size of this region. Okay, if we need that the full region, let's say that here at the peak the full region was emitting at maximum, okay, and here the emission of the full region was negligible. This kind of this process here, it takes some time to happen. You cannot do like that and a region of a few light hours or light days instantly emit. Okay, so there is some time for the information to propagate in an emission zone. It can be, for instance, a blob going up an AGN jet. Okay, so it takes some time. And if we approximate this as the speed of light, like we assume, we take this as the maximum possible speed for information transfer, then we can set this can associate this time scale to the size of the object. Okay, so it's in principle it's trivial. So the size of the emitting object has to be smaller than the speed of light times the time scale of variability. Okay, things get a bit more complicated if we are working with in the cosmological scale. So the dt that we observe is what we call the observed in the observer frame, and then we have to correct it for the redshift. Okay. So if you measure the time variability, the time scale variability in an AGN in a redshift 1, actually the upper limit will be half of what it would be at a redshift 0. Okay. And furthermore, if the emitting material is being ejected in our direction, like a relativistic jet, we have to correct for the Doppler factor. Okay. Otherwise, we see these superluminal motions. Okay. Okay. This kind of estimate here is very important. Especially of size estimate is very important, especially for the corona. Let's go a bit deeper in the corona. So a considerable fraction of the energy of many AGNs is emitted in X-rays from 0.2 to 100 Kelvin. Kiloelectron volts. And we observe this X-ray emission to have very, very short variability time scales. Okay, so we have flares that last just I don't know, minutes, hours. Okay, and these time scales are smaller than the size when you multiply by the speed of light, are smaller than the estimated size of the disks. They are much smaller. So there is something emitting the X-rays in AGN which is coming from a region which is smaller than the disk. Okay, we don't know exactly the shape of the corona, but we know that it's smaller than the disk. Okay, because of this kind of approximation. And moreover, the shape of the spectrum, as you can see here, is very different from the integrated black-body spectrum from the disk. Okay, so we really know that there is something else there, something beyond the disk that is producing these X-rays. That's what we call the X-ray corona. Thus, the origin of energy X-rays cannot be the disk itself. Yes, a plausible idea is a hot dilute gas in which the soft disk is disk emitted photons are upscattered to the X-rays in the corona. Do you remember from the previous classes where we briefly mentioned what causes the shape of the spectrum of the corona? Do you remember the emission process that we learned up to now? Do you remember? Synchrotron radiation, synchrotron self-Compton. We have external Compton. It has to do with Compton. We learned bremsstrahlung. This actually X-rays in AGNs can come from bremsstrahlung, but in this case, this is not the answer I'm looking for here. And do you remember we talk about Comptonization? Do you remember? It's inverse Compton. However, several times. Okay. So this is the Comptonization spectrum. This is for an AGN with a Shakura-Suneev disk. Okay. If you have a RIAF, you can have a bremsstrahlung emitting the X-rays. Okay. So here I'm showing you some possibilities for the coronal configurations. So you can find several of these in the literature. You can find this sort of crown, like corona, in black holes. You can find this what we call the sandwich corona. You can find this spherical corona, of course, imagine in 3D here, so it's a sphere. Or the toroidal corona, imagine this the donut around the black hole. So there are several possibilities. So don't take a single picture at your mind. This is the black hole corona. No, actually, the exact shape we don't know. Okay. But we imagine something like the solar, more or less solar corona in one of these geometries. Okay. Okay. Yeah. So far we discussed mainly the thin accretion disks and briefly discussed the RIAFs, the radiatively inefficient accretion flow. There is other possibility actually for accretion disks, which we call slim disks, or also thick disks. And they can happen when we have a lot of material being accreted. So the accretion, in terms of Eddington luminosity, the accretion range at which we have the Shakura-Suneev disk, roughly speaking, comes from 1% of the Eddington accretion rate up to 30% of the Eddington accretion rate. You can go a bit over, a bit, it can be a bit lower, okay? We don't have a precise number. But above this 30%, 50%, we can have some very peculiar things happening in the disk. The temperature of the disk rises so much, actually not rises, but the amount of photons is so much that the radiation pressure can, how do I say, puff up the disk. Okay, so we can have this fat disk, this large, thick disk around the black hole with a lot of accretion. And actually, at some point, since it's covering most of the black hole, and this is a lot of matter falling down, the opacity here is still very high. It's like black body opacity. So the photons take a lot of time to travel through the disk. Okay, if this travel time is larger, the time scale for this travel time is larger than the accretion time scale, this material, together with the light, will be swallowed by the black hole before emitting the radiation. So the radiation efficiency drops. This is what we call the advection. This black hole is advecting, is without giving the chance for this radiation to be emitted. Okay, so in this kind of disks, we have a lot of accretion, but they are not very efficient in terms of luminosity. Okay, these are the slim disks. And okay, the simple hydrostatic solution no longer holds, and then this fraction here, h over r. H is the height, the scale height of the disk, and r is the distance from one point here to the black hole. This scale will grow a lot. Okay. Of course. Here in this edge, you see that the disk becomes the Shakura-Suneev disk again. Okay, so this this thick part of the disk is closer to the black hole, where the radiation pressure is much more intense. Okay. I think this is all what I already said. Yes, photons are created in the radiation pressure dominated region, are trapped by the accretion flow, and this term you hear a lot in Newtonian physics, they were advected, they were swallowed directly to the black hole, and the result is a very inefficiently disk in terms of radiation emission. Okay, there are systems where the flow is adiabatic due to very low accretion rate, which means that they are going to be swallowed without emitting radiation. Okay, and the Coulomb efficiency in most of the processes in the accretion disks depends on the electron density E squared. If we have a disk that is accreting very slowly, is very we don't have enough mass, we don't have enough accretion rate. Okay, then the density of electrons will drop, and then the efficiency of cooling will drop with the square of this. Okay, so accretion disks at very low accretion rates have much lower densities and hence cooling times which are equal or even exceed the inflow time scale of the gas. And the temperature in such cases, because the cooling time scales are very long, the temperatures they are just rising and rising and rising until they reach the virial temperature of the system. If they increase in temperature, they just escape the black hole, okay, the region around the black hole. But they will grow in energy, in temperature, until reach the virial temperature. So in the virial temperature, the potential energy, the gravitational potential energy, is comparable to the thermal energy of the particle. Okay, then this ratio will be 1. So this over this, no? Over 3 kBt over 2. This will be 1 if we isolate T for a supermassive black hole. It will give us a plasma with 1 trillion Kelvin. It depends on the mass of the black hole you put there, of course, but 1 trillion Kelvin, it's a lot. This, however, is for the ions. The electrons have 1,000 less mass, and then the temperature for the electrons will be 1,000 smaller, 1,000 times smaller. Okay, so this is a characteristics of the RIAF systems. Actually, this is under discussion, but there is this discussion on this 2 temperature plasma orbiting following the black hole in RIAF systems. 1 trillion Kelvin, it's a lot of Kelvin, no? So, this is what we call hot accretion disks. The other ones, the Shapura-Sunyaev disks, we typically call them cold accretion disks. Even if the temperature there can reach 100,000 Kelvin, we call them cold accretion disks. Okay. Okay. Such a flow can be a combination of standard, in the case of the RIAF, can be a combination of a standard thin accretion disk, as you can see here, with this thick, very hot and inefficient accretion disk that will extend towards the black hole until the ISCO. Okay, what's the ISCO? Yeah, this is usually referred as a two temperature disk. I was talking about 2 temperature plasma before. This is another thing, 2 temperature disk, and is one of the suggested models for low luminosity AGN. However, checking this is more complicated than it sounds. Yeah, the models for low luminosity AGNs, it's very hard to find the data that really support them. Okay, but we give our best. And the threshold accretion for the RIAFs to start is Eddington. This is in terms of the Eddington accretion rate. So it's an accretion of 1% of the Eddington accretion rate. Okay, below that, we start to see these RIAF systems. Okay, here you can see it's called ADAF. ADAF is a special case of the RIAF. What we call advection dominated accretion flow, but everything is RIAF, okay? Okay, how many of you have heard about magnetic pressure? Except for you, because I know that you heard about it. Have you heard about magnetic pressure? Have you heard, Paolo? Maybe. Magnetic pressure. Magnetic forces are very tricky, because they kind of, well, they will not accelerate particles parallel to the field lines. There is always this direction component that makes things tricky in with magnetic fields. But let's go slowly here. So we have the Lorentz force here that you all know, but in AGN disks we are more interested in the populations, in the fluxes, okay, flux elements, instead of looking for individual particles. Okay, so let's rewrite this, which is the force, the Lorentz force, in terms of the force density. Okay, so let's define, we can multiply everything by the electron density, and then we have that the density of electrons is NQ, should be here, and you have that if we multiply NQV, we have the current density. Okay, actually we can cut off the electric field component. We are assuming because we are going to assume a magnetostatic approach just to facilitate. Okay, so the Lorentz force becomes this. This is the force density. Okay, it will be very useful for us. So okay, so the force density is simply the current density vector product with the magnetic field. But actually we can recover the current density from Ampere's law. From Ampere's law, we find that we isolate J here, and we find that the current density is given by this expression. Substitute this in the force density equation, we have this, and then we can use this vector identity here to find this result. Okay, this result, from this result we can extract some things, we can interpret them. For instance, here, this is force per volume, okay, force density. Here we have a gradient, so it's something over distance. Okay, this has to be force over area. Okay, force over area, pressure. Okay, this one is a bit more complicated to interpret. I'll just throw it to you. This is the magnetic tension. At the moment, let's focus on this. Okay, this is the magnetic pressure. We can write it like this. Okay, one particular characteristics about magnetic pressure is that it's direction dependent, like everything in with magnetic fields. Okay, so imagine you have several magnetic field lines here in the vertical. If you manage to squeeze them in a region, they will start making pressure to relax again. Okay, you can for the tension is a bit different. The tension will act to keep the line straight and not stretched. Okay, not curved, not stretched. So if you curve a magnetic field line, this tension force will try to make it straight. Okay, if you instead take imagine it as a string, take the magnetic field line and stretch it like this, the magnet tension will make it come back. Okay. Okay, have these two things in mind. Okay, this is an example. For instance, if the lines were bended in this direction, the magnetic tension will try to make them straight again. Okay, we'll try to push them in that direction. So if you put something here that pushes the magnetic field lines will act against trying to push it back. Okay. Okay. Okay, this is the things I told you before. And now that we have this concept in mind, let's talk about magnetorotational instability. You have a question? No. Okay. You did like that. Let's talk about magnetorotational instability. I told you in the beginning of this class that if you don't have magnetic fields in an accretion disk, the accretion is very inefficient. Okay, the disk is very stable. It basically doesn't fall. The matter is not falling in the black hole. However, if you have magnetic fields, they don't need to be very strong. For an AGN, it can be a few Gauss. Okay, and if you have matter here attached to the magnetic field line, which can be the case of a plasma. A plasma, we have this phenomenon called magnetic field freezing, where the plasma is connected, is glued to the magnetic field. So if the plasma goes to this way, it brings the magnetic field with it. Okay. If the magnetic field goes in the other way, it brings the plasma with it. Okay. This is the magnetic freezing. Okay. So imagine an AGN disk. We have a particle in an internal ring, which is orbiting the black hole faster than a particle in an external ring. Fine, no? Imagine that these particles are connected by a magnetic field line. If you stretch this magnetic field line, the magnetic tension will pull this, like trying to break it. No, wait for me, no? And this other one will be pulled, okay? So this particle here will lose a lot of angular momentum for this particle here. So these external particles are gaining angular momentum. As we chatted, you asked a few classes ago how the winds were formed, and I told you, there is radiation pressure, but that there is also momentum transfer from the accretion. No? This is very efficient for transferring angular momentum from the inner parts of the disk to the outer parts that can be then blow up from the region around the black hole. So this will give angular momentum to the external particle and remove angular momentum from the internal particle, which can then fall more efficiently closer and closer to the black hole. Okay, and this is allowed only if we have magnetic fields. Okay, this is another picture of the process. So you have these two particles that started in the same point, this giving a face-on view instead of a profile view. So this comes with a higher speed. At this point, the magnetic tension is pulling them together, and what happens is that the inner particle will fall in orbit and the outer particle will grow in orbit. Okay. It's clear the magnetorotational instability. Okay, we also have this is a very, very important phenomenon to mention, which we call the magnetically arrested accretion disks. Okay, and now it will be very useful to understand the magnetic pressure. Let's try to follow this. To follow me, you too, everybody. We have matter falling in the black hole. Matter that is attached to the magnetic fields. Over time, as the matter is following the black hole, it's bringing magnetic field lines towards the black hole. Okay? Then what happens to the magnetic pressure? Here is the black hole, we are packing the black hole, the surroundings of the black hole, with a lot of magnetic field lines. What happens to the magnetic pressure here? It will increase in this direction, which is the same direction of the infalling gas. Then we can arrive at this state that we call the magnetically arrested disk, where the magnetic field starts to dump, to break the accretion. Okay, it's a sort of equilibrium. It's enough. No more accretion. Okay. So this is what we call the magnetically arrested disk, and this is also the engine behind the jets in AGNs. The jets. Now I don't remember. I can show you this. It's better if I show you this simulation a little, and then I go to the next slide. No, I remember now. So this is a simulation done by Professor Sasha Tchaikovsky, which is one of the world leaders in the field. And you see, let me see if it's in enough resolution. These are the magnetic field lines. Can you see it? Okay, we have magnetic field lines going that direction. They are attached to the plasma. Okay, the disk is not, there is no accretion yet, but the accretion is going to start. Okay, the disk is starting to fall in the black hole. And this, in this plot here on the right, you see another perspective of the black hole, looking it from face on. Okay, from the rotation axis. Okay, and you can see that the magnetic field lines already start to turn. Okay, so in the beginning is like that, they are radially pointing. Okay, so as the plasma rotates around the black hole, we see that these magnetic field lines coil around the black hole. Okay, so there is some accretion happening, and at some moment we see the formation of the relativistic jet, which is basically this blue thing you are seeing there. You can see here on the right that the magnetic field lines are doing this coil, while here you can see that the magnetic field lines are pointing up. This is called magnetic buoyancy. Okay, so you have a lot of magnetic field rings after coiling, packed around the black hole, and then the magnetic pressure, boom, shoots them up, okay, or down. Okay, so this is just to give you an idea of accretion and jet formation. So we have two competing physical effects. So we have the dragging and coiling of the magnetic fields by the accretion disk going around the black hole, and we have the buoyancy that I just mentioned, or relaxation, shooting these rings of magnetic field lines. Okay, and at this point you realize it's obvious, no? That tell me if it is obvious that to have jets you need rotation. Okay, and actually these jets, they are very, very efficient in rubbing and taking rotational energy from the black hole. Okay, so the black holes will become slower because of the jets. Okay. Okay, so when does the MAD happen? The MAD is the magnetically arrested disk, no? This limit where the accretion is starts to be blocked by the magnetic field. It happens when this dimensionless magnetic flux that we define as phi reaches a value of 40 or 50, more or less. This is achieved through simulations, okay? And the dimensionless magnetic flux is defined as the magnetic flux, which is the integral of the magnetic field across a given area, divided by the square root of accretion, gravitational radius square, and the speed of light. For a stellar mass black hole, the needed magnetic field to reach the MAD state, the magnetically arrested disk state, is of the order of 10 to 8 Gauss. It's a lot. It's not a neutron star-like. It can be a very old neutron star-like surface magnetic field. But for a young pulsar, this is nothing. And however, for a supermassive black hole, it can be of the order of 100 to 1000 Gauss, or even less. Okay, so 100 Gauss, it's not that much, no? It doesn't feel that much for such extreme phenomenon, no? But remember that the larger is the mass of the black hole, the larger it will be its area, no? That the area will grow with the square of the mass. So you have a weaker magnetic field, but you have a huge area permeated with this magnetic field. And finally, this is actually my last slide, and it's just to. We are not going to use this here, but I think it's important to tell you about this. This is the plasma beta parameter. You see this everywhere in plasma astrophysics, okay? Okay. And this beta is this dimensionless number that tells you who is winning between the gas pressure and the magnetic pressure. It's very important, for instance, for the formation of stars. When a nebula is collapsing, magnetic pressure there can act against the formation of stars. And it's defined as the gas pressure over the magnetic pressure, okay? In the simplified form, it's defined like that. NKBT over B squared 2 mu 0. The magnetorotational instability that I mentioned for the accretion disks in AGNs is best when beta is relatively high, so 10 to 100, okay? Which means that the gas pressure is superior, is over the magnetic pressure. But the magnetic pressure is not negligible, okay? It can be 1% to 10% of the dominating pressure in the disk, okay? However, as we discussed, if the flux accumulates near the black hole such that the magnetic pressure grows a lot, then beta decreases a lot. The accretion breaks because the magnetic pressure is now stronger than the gravitational room pressure of the infalling gas. And here I give you some examples of where to find the different values of beta. So beta very small, you can find it in solar corona or in AGN relativistic jets. Beta of the order of 1 you can find in AGN disks or in the interstellar medium, for instance. And beta much larger than 1 you can find in the interior of stars, for instance, and the outer denser regions of accretion disks. Okay, and that's what I have for today. Do you have questions? Everything clear? Marcela?
I'm trying to enunciate where I have to ask.
You have the doubts, but you don't have the questions. I see. It happens to me a lot.
I was intrigued when you said that the black hole eventually loses gravitational energy when this process, but it should be like an amount. It should not be a continuous thing, a continuous process, because it needs to still happen for the jet to be known. not lose that much rotational energy.
No, okay. That is a limit. You can, for instance, for a maximum spinning black hole, I don't remember exactly the numbers, but you can extract up to 30% of the rotational, of the angular momentum of the black hole with this process. The name of the process, actually, I'm not detailing the process here. The process, which is actually stealing energy and angular momentum from the black hole, is called the Blandford-Znayak. And yes, it can
because I thought if you remove a certain amount, then you will fall out of the equilibrium of the system, and then you should have no jet.
Yeah, but this can happen.
You lose the jet.
The jet stops. This can happen.
This happens?
Yes.
What?
The jets can stop as they can start. They can stop.
I see. I thought that they were just like, once there's a jet, there will always be a jet.
No.
Makes sense. So if it reaches a certain threshold of these angular loss and angular momentum, then no more jet.
No more jet.
Okay, that's shocking. I will have a hard time sleeping tonight. I have some questions from the previous lesson.
Sure.
Specifically about the hands-on exercises. I was having some trouble in lesson 3 when it was to get the delta E over E calculated.
The Dirac delta. Do you have it there?
The exercise.
Okay.
I'm having some trouble on how to obtain this delta E.
How to obtain the delta E?
Yes, from the energy using this.
Okay. Because I think you have something like that. I remember the problem correctly. You have something like this is a final energy over the original energy. It will be equal to 1 plus some fraction, something here and something here. Do you arrive at something like this?
Yes.
Okay, then if you pass the 1 here, it will be EF minus E0 over E0. Okay, then this is the delta. Okay.